Input systems are fundamental for creating interactive applications and games in C#. They enable users to engage with software through various devices like keyboards, mice, and touchscreens. Mastering these systems is crucial for building responsive and dynamic user experiences. Effectively capturing and responding to diverse inputs is crucial for crafting engaging and intuitive user experiences. This involves understanding the action's context and providing immediate, meaningful feedback, ensuring a smooth and enjoyable interaction with your application. While Unity offers a built-in input manager for new projects, the dedicated input system package is recommended. This newer system provides more flexibility, better performance, and a robust architecture for managing complex input schemes across multiple platforms. Capturing keyboard input involves detecting 3 states: pressed, held down, or released. These distinct states are essential for implementing various game mechanics, from single-action commands like jumping to sustained movements, providing granular control over user interactions. The input.getKeyDown method returns true only during the single frame a key is initially pressed. This is perfect for instantaneous actions that trigger once per press, such as making a character jump or toggling a menu, preventing accidental repeated actions. For continuous actions requiring sustained input, like character movement or accelerating, input.getKey is ideal. This method returns true for every frame as long as the key remains held down, allowing for fluid and responsive control over ongoing processes. Finally, input.getKeyUp detects the exact moment a key is released, returning true only during that specific frame. This is useful for actions triggered upon input cessation, such as stopping a sprint, releasing a charged attack, or confirming a selection. To illustrate these concepts, let's examine a basic C# example demonstrating these fundamental keyboard input methods within a Unity script. This code snippet shows how getKeyDown, getKey, and getKeyUp are used together to handle various user interactions. Notice how debug log statements confirm when each key state is detected and processed. These log messages provide invaluable, immediate feedback in the Unity console, allowing you to easily verify input logic and aiding in debugging during development. When handling keyboard input, always use the key code enumeration to specify individual keys. This ensures superior clarity and consistency in your code, making it more readable and maintainable than using magic numbers or strings. Key code provides a type-safe list of all possible keys. It is critical that these keyboard input detection methods are called from within Unity's update function. Update is invoked once per frame, ensuring your application continuously checks for and captures user input at the highest possible frequency. This guarantees responsiveness and prevents missed key presses. For more advanced and configurable input, especially with gamepads, consider input.getAxis and input.getButton. These methods allow mapping physical inputs to named actions defined in Unity's input manager. This provides greater flexibility and easier remapping for users. Now, let's shift our focus to mouse input, another fundamental interaction method. We will cover detecting button presses, accurately tracking mouse position, and responding to mouse wheel movement. This equips you with comprehensive mouse interaction capabilities. The input.getMouseButtonDown method returns true only during the frame a specified mouse button is initially pressed. The button parameter uses integer values, 0 for left, 1 for right, and 2 for middle, allowing precise control over which click you're detecting. Similar to keyboard input, input.getMouseButton returns true for every frame as long as the specified mouse button remains held down. This is ideal for continuous actions such as dragging objects or drawing lines, providing sustained control within your application. Conversely, input.getMouseButtonUp registers the exact moment a mouse button is released, returning true only during that specific frame. This is useful for actions that conclude upon release, such as completing a drag-and-drop operation or finalizing a selection. To accurately determine the mouse's current position on the screen, use input.mousePosition. This property returns a vector-3 value, where x and y represent the mouse's pixel coordinates, with the bottom left typically being. The z component is usually 0 for 2D screen space. Let's now look at a straightforward C# example demonstrating both mouse input detection and position tracking. This script combines the methods we've discussed, showing how to respond to mouse clicks, while simultaneously capturing and utilizing the mouse's screen coordinates. This code logs the precise mouse position to the console whenever the left mouse button is pressed. This immediate feedback is incredibly useful for debugging and understanding mouse coordinates. Such functionality is vital for object selection and UI element manipulation. When clicking on specific objects in a 3D environment, combine input.getMouseButtonDown with a raycast. A raycast is an invisible line projected from the camera through the mouse's screen position into the 3D world. If this ray intersects an object, you can detect that interaction. Mouse input is also vital for interacting with user interface or UI elements. It allows users to trigger events such as button clicks, manipulate sliders, or perform complex drag and drop actions within your application's menus. Proper mouse integration ensures a smooth and intuitive experience. Transitioning to mobile platforms, touch input is indispensable and the primary interaction method. It allows for intuitive and direct manipulation, supporting single-touch gestures and complex multi-touch interactions like pinching, rotating, and swiping. Understanding touch input is key to creating engaging mobile user experiences. The input.touchCount property provides the exact number of active touches currently present on the screen. This value is crucial for determining if any touch input is occurring and for iterating through multiple touches, allowing you to handle single-touch or complex multi-touch gestures effectively. To access detailed information about each individual touch, use input.getTouch. This method returns a touch struct, a comprehensive data structure containing various properties about a specific touch. By providing an index, you can retrieve data for each finger currently interacting with the screen. The touch.phase property indicates the current state or lifecycle stage of that specific touch. This includes began when the finger first touches, moved as it slides, ended when it lifts, stationary if held still, and canceled if interrupted. Understanding these phases is vital for precise touch gestures. Another critical property within the touch struct is touch.position, which provides the precise screen coordinates of where the touch occurred or is currently located. These are pixel coordinates, with the bottom left typically being. This position data is essential for tracking finger movement and enabling drag and drop. Let's explore a C# example demonstrating how to handle single touch input and accurately detect its various phases. This script will illustrate the practical application of input.touchCount and the touch struct, showing you how to respond to a finger touching, moving, and lifting from the screen. This script logs distinct messages to the console for each phase of a single touch, when it begins, moves, and ends. This provides clear, real-time feedback on the touch events, allowing you to easily verify the logic and understand the flow of touch interactions, invaluable for debugging. For practical applications, leveraging the touch.phase property is fundamental for implementing common mobile interactions like tapping or dragging objects on the screen. By checking if touch.phase is began for a tap or move for a drag, you can precisely control how your objects respond to user input. For complex interactions, multi-touch input can be handled by iterating through the input.touches array, which contains a touch struct for each active finger. This array allows you to process multiple touches simultaneously, enabling sophisticated gestures such as pinch to zoom or two-finger rotation. When developing for mobile, you can simulate touch input directly within the Unity editor using your mouse. This means you don't always need a physical device for initial testing. By configuring the editor, you can use mouse clicks and drags to mimic single or multi-touch gestures, streamlining development. Furthermore, ensure touch inputs are correctly recognized and respond appropriately on all user interface elements. This includes buttons, sliders, and scroll views. Proper integration with Unity's UI event system ensures that taps and gestures on UI elements are handled smoothly and intuitively, contributing to a polished user experience. Mastering input systems in C# is crucial for creating interactive and engaging applications across various platforms. Whether building for desktop, web, or mobile, The ability to effectively capture and interpret user input is paramount to delivering compelling software experiences that truly stand out. By understanding how to capture and intelligently respond to keyboard, mouse, and touch inputs, developers gain the power to build an incredibly wide range of interactive experiences. From fast-paced action games to intuitive productivity tools and immersive simulations, your mastery of input systems unlocks limitless creative potential. We've covered the fundamentals of detecting key presses, mouse clicks, and touch phases, along with practical C# examples for each. We explored methods like get key down, get key up, get mouse button down, get mouse button up, and the touch.phase property, providing a solid toolkit for input handling. Now, with this foundational knowledge, we strongly encourage you to actively practice implementing these input methods in your own projects. Experiment, build, and iterate to truly solidify your understanding and unleash your creative potential. The more you apply these concepts, the more intuitive and powerful your interactive applications will become.